Hello dear students, welcome you all. In today's lecture, we are going to discuss high pass filters, right? High pass filters, right? And we know that we are discussing high pass filters of Butterworth type. Clear? Butterworth type high pass filters, right? In previous lectures, we have discussed about the low pass filters, right? We know in case of low pass filters, uh, the frequency response was like uh, it was in case of low pass filter, the frequency response was like this. Clear? This is the case of this is gain versus frequency. Clear? This is the case of low pass filters. Clear? Here this frequency corresponding to this is FH, the highest frequency that is allowed to pass from the filter, and all the frequency toward this side of this region are attenuated or stopped by this low pass filter. But here we are going to discuss the high pass filters. So if I draw the frequency response of high pass filter, it will be exactly opposite to it. Clear? In case of high pass filters, we will have frequency response of right this type. Clear? And this is the frequency corresponding to this point is called FL, right? The lowest frequency that is allowed to pass from this filter. Clear? All the frequencies toward this side are allowed to pass from the filter, whereas all the frequencies below this frequency toward this side, they are attenuated or stopped by this high pass filter. Clear? This is the frequency versus gain uh, graph, right? So this is the frequency response of a high pass filter. So we can see it is exactly opposite to the low pass filters, right? Now we will start with the Butterworth type high pass filter of first order. Clear? We will take the case of first order. Clear? First order means we are going to use only one filtering unit here. So for it, we are going to draw the circuit diagram first. Then we will go to the next steps. So first of all, we are going to take a operational amplifier. This is the circuit diagram. This is the feedback path. Clear? Right? Uh, we are going to connect input signal at this terminal of the right. So there will be the resistance. In this case, the filtering unit will be exactly opposite to the case of low pass filters. means we will have capacitor first and then we will have a resistor. The capacitor will be here. Right. And here we will have this is resistor. This is again resistor, RF feedback resistor, R1. This terminal is as virtual ground. This is again at virtual ground, and this is capacitor C. This is resistor R. Clear? This is node 1. This is node 2. Clear? Let the voltage at node 1, or we can say at this point it is B1. Clear? Here we are going to apply the input signal, but before that, this is negative, this is positive, right? It is plus BCC minus BEE. Clear? This is V output, and we are going to connect load resistance here. Here we will have input signal, this is for input signal B in plus minus. Clear? This is load RL. Clear? The gain of this amplifier. Right now, this is the circuit diagram for this high pass filter of first order. First order means we have only one capacitor and one resistor. This is the filtering unit of this high pass filter. This is operational amplifier working in non-inverting mode. Again, if I write down the expression for the output of this operational amplifier, that is equal to 1 plus RF over R1 into B1. Clear? B1 is the voltage appearing at node 1. Clear? So the same thing that we are going to do here. First of all, we are calculating the value of V1, and then we will put this value in this equation, and we will find the expression for a transform function, that is B output upon B input. Clear? That will tell us about the frequency response of this filter, right? So to find the value of B1, let's suppose this circuit, current I is flowing here. So the same current is going here and here, I. Because we know toward this side, the current is nearly equal to 0. Clear? I is nearly equal to 0, as I told in the earlier lectures. So current I started from this point, from the signal, input signal, it flow in this path and ultimately it arrived at this point. Clear? So to find the value of B1, we have to consider this loop. Clear? This loop, right? And we have to apply the loop rule here first. So according to the loop rule, the different voltages that are present in this loop are B in minus plus. Now current is going in this way, so it is positive, it is negative. Clear? Minus iota XC into I. What is iota XC? It is the capacitive reactance, but it is basically what is capacitive reactance? 1 upon 2 pi iota FC. So I am taking iota in the denominator, so obviously it will become positive. Clear? Then the next voltage in this circuit is minus IR, because current is going in this way, so same logic is here, right, is equal to 0. We started from this point, negative positive, here it becomes positive negative because current is going toward this side, same logic is here, so this is equal to this, plus minus, it become plus because of iota, and then minus is equal to 0. So it becomes B in is equal to I into R minus iota XC. Clear? R minus iota XC. Right? So I is equal to B in upon R minus iota XC. Clear? So now this equation I is equal to this. Now we are going to utilize this equation in this loop. Voltage B1 is equal to IR. So B1 is equal to I means B in upon R minus iota XC into R. Clear? So now I am going to simplify this equation. Clear? So when we will simplify it, it will become B1 is equal to B in R upon R plus 1 upon 2 pi iota FC. I can write it in more clear way. FC. I took iota in the denominator, so it becomes positive. 1 upon 2 pi iota FC. Then I will take the LCM, multiply it here and multiply it. Then this equation will become 2 pi iota R FC divided by 1 plus 2 pi iota R FC, right, into B in. Clear? B1 is equal to this. Clear? Now we are going to put this value of B1 into this expression. Clear? That is V output is equal to AF into V1. V1 means 2 pi iota RFC divided by 1 plus 2 pi iota RFC into B in. Clear? So I can take that B in toward this side, so it will become divided by B in. So I can erase it from here, right? So now this is the more simplified form. So I can further modify it. I can write it is equal to AF into F upon FL iota denominator 1 plus iota F upon FL. Here FL is equal to 1 upon 2 pi RC. Clear? 1 upon 2 pi RC. So if you will put it here, you will get the same thing. Clear? So this is B output upon B input. Sorry, B input. Now what is it? It is the expression for a transformer function. Clear? B output upon a B input. Here FL is called the cut-off frequency in this case, lowest frequency that I talk about in the beginning, right? When I draw the frequency response. Clear? FL is equal to this. Clear? Now, if I take the magnitude of this side, B output upon B input, then it will be obviously a F upon FL bracket magnitude only 1 plus F upon FL whole term square and under the root. Clear? Because here we have when you will take the magnitude of numerator, magnitude of a denominator. Magnitude of denominator becomes this, denominator 1 square plus this square whole term under the root. So this is the transform function magnitude, right? This is equation number 1. Now this is the expression that we were looking about at the beginning when we have drawn this circuit. This expression is telling us about the frequency response. If I plot this B output upon B input versus frequency, then I will get this type of graph. Right. This is the right. This is the graph. This is frequency toward this side and gain. B output upon B input, gain toward this side, and this is frequency, right? So this is the frequency. This frequency, this one will corresponds to FL. Clear? Now let's see. This is the ideal case. Clear? Now let's see if F is very less than FL, right? If F is very less than FL, then this term can be ignored, right? So it means we will have a under root 1. Under root 1 is 1, obviously. In this case, F is very less than FL. It means this term is again a very small quantity and it approaches 0. As the F approaches 0, so we got this line when F is very less than FL. But as F becomes equal to FL, here it will become 1, here it will become AF divided by under root 2. Clear? That is 0.707 AF. So this is what I have here. F is equal to FL 0.707 AF, and this is AF. Clear? Ideal response means when frequency is very high, right? Then this gain becomes maximum. Clear? But in reality we are following this line. So now the next condition is when F is very greater than FL. So in that case, if F is very greater than FL, yeah, higher than FL, then I can ignore this 1 as compared to this term, right? Then under root of this term will be some number, right? Greater than 1. Clear? And it is obviously F is greater than FL, so again it is a number. So we will get a number that is more than a FAF. Clear? So FAF will be multiplied by some factor, so we will get this response. Clear? In this case. So here you can separate these two bands. This is pass band, and this is a stop band. Clear? Here we have F in the denominator as well as F in the numerator. So the significance of it is that as the F increases, so F increases in both denominator as well as a denominator. So it will stop this side from rising continuously. Ultimately, they will attain a equilibrium condition in which we get the ideal response that I talked about in the beginning, that this is the ideal response, right? But otherwise it will be not straight line in such a way, but it will have some curves, right? So this is but one thing is sure, that as f is greater than fl, so this term is stable, right? And it is increasing, but it is not decreasing. It is increasing, and ultimately it is going to become stable. But f, as the f is approaching this side, f is less than fl, then in that situation it is decreasing. Now the roll off rate, the fall rate of this gain, it is, in this case again it is a first order filter, so it is minus 20 decibel per decade. Clear? So again the same thing that was in the case of low pass filters. The roll off rate is same. In case of first order low pass filter, it is minus 20 decibel per decade. Clear? We will see that in the case of second order it will become double, right? So this is about the uh, Butterworth high pass filter of first order. Clear? This is a circuit diagram. We simplified the circuit diagram by finding the voltage at this node 1, that is B1. Then we put the value of B1 here and we got B output, right? B got B output upon B input. Then we simplified it. We find the value of FL, cutoff frequency 1 upon 2 pi RC, and then ultimately this is the transform function, right, that we have plotted here. Now you can check all these graphs by plotting these graphs on LT-Spice simulator, circuit simulator. You can design this circuit on the LT-Spice. LT-Spice is basically a circuit simulator. LT-Spice. You can design this circuit on the LT-Spice, and then you can put the value of R1, RF, all these values, and then you can simulate. Simulate means you can plot this graph. Clear? You will see, you can verify that this graph will be of this type, and with the roll off rate, all the things will be same, nearly same, that are predicted theoretically. So you will get all these results on a LT-Spice, right? So this is all about high pass filter of first order, right? So in the next lecture we will discuss about the second order. Clear? So thank you very much.